All right, welcome back, guys. This will be our last section in Chapter 4, Section 4.3. And in this section, as we've been alluding to, we're going to talk about how strong the correlation between two data sets is. In 4.1, we introed scatter plots. We looked at positive correlations versus negative, strong correlations versus weak correlations. And then we dove a little deeper in 4.2 into trend lines and how when we put a trend line on a scatter plot, we can use it to estimate data points, how accurate that trend line is going to be, et cetera, et cetera. How do we find the values of a trend line? In 4.3, we're going to dive more into how do we come up with correlation. We know how to identify whether it's strong, weak, or moderate just by looking at the scatter plot, whether it's positive or negative. But how do we physically quantify it? What's the difference between a strong correlation and a really strong correlation? And that's what we're going to talk about in 4.3 today. We're going to do this by finding the correlation coefficient R. Okay? R is the variable for correlation coefficient. Essentially, there is a mathematical way where we can calculate how strong or weak the correlation between two data sets is. Correlation being a fancy word for relationship. Okay? So let's dive into this. Well, let's go back to a reminder about correlations. And I would pause the video and write each of these down just so you remember kind of where stuff's at. Remember, a positive correlation, it looks like this. Here are some data points. And what we see with a positive correlation is for a high value in one data category, we have a high Y value. If we have a low value in one category, we have a low value in the other. This can be seen here. For a low value of X, I have a low value of Y. For a high value of X, I have a high value of Y. Obviously, it's not a direct relationship, but it's pretty close in general. As one increases, so does the other. The real world example you could think of is the amount of hours I work. Let's say this was hours I work and money I make. Okay, that would probably be closer to a direct relationship. You could also use the amount of time studying and the grades on a test. Okay, positive correlation. It doesn't mean there are never low X values or low values in one category, right? If you don't study much, you'll still get a low grade. It just implies that if one's low, the other's low, and if one is high, the other is high. A negative correlation, on the other hand, implies the opposite. Again, you can imagine it to look something like this. They will be opposite. If one is low, the other's high. If the other's high, the one will be low. Imagine temperature and amount of snow. When the temperature is really low, the amount of snowfall could be high. When the temperature is very high, snowfall is going to be at a low. Another example you could think of, the amount of money I have in the bank versus the amount I spend. As one increases, the more I spend money, the amount of money in my bank will decrease. The less spending I do, the more money in the bank. There's an opposite relationship. If there's a low X, there's a high Y. If there's a high X, there will be a low Y. And then no correlation. No correlation, as you well know, we're going to see values all over the map. Again, please write these definitions down. This is going to be a mixture. It doesn't really follow a rhyming pattern. It's not that as if X is low, then Y is low, or if X is high, then Y is high, or if X is low, then Y is high, or vice versa. There's no pattern to it. One thing you could think of here is the speed of the wind and the amount of time I spend in the office. The speed of the wind and the amount of time I spend in the office, okay? Some days I don't spend as much time in the office and the wind could be high. Other days they don't spend much time and the wind could be low. They don't really impact each other. You could have some high values for X and low values for Y, but you could also have some high values for X and some high values for Y. There's no rhyme or reason to it, no correlation. Okay? So that's a review of correlation, high, moderate, and low. But where does the equation for R come from? I've alluded to that there's a way to mathematically quantify what's strong correlation and what's weak correlation. Well, R is the unitless mathematical constant representing correlation strength. In other words, the correlation coefficient. So where does it come from? I will warn you, this is going to be some bulky theory. Do I want you to write it down? Absolutely. This is going to help you understand what a correlation coefficient is. But are you going to necessarily apply this a ton? No, not directly. We're going to talk about some background of R, then we'll get into how do we calculate R. So where did this formula come from? Mathematicians and statisticians sat there and they said, we want a way to quantify how strong or weak the correlation is. So what did they do? Well, if we look at a scatter plot, and I've got data kind of all over this scatter plot, you could probably tell me that my mean Y value would be somewhere in here, and my mean X value would be somewhere in here. This point here in green would probably be X bar, Y bar. So how do we figure out how strong or weak the correlation is? Well, we can start out the process by taking all of our data values and subtracting it from the mean. And then we multiply them together. Okay? If my X value creates, X minus X bar creates a positive value, then it is a high value for X, and will end up on this end of the spectrum. If it is a low value for X, it'll create a negative value, and it'll be on this end of the spectrum. Same with Y. If Y minus Y bar produces a negative value, then Y is on this end of the spectrum. If it makes a positive value, it's on this end of the spectrum. Okay, so they started there and said, well, let's take all our data values and subtract them from the mean. Then what we're going to do is we're going to multiply them together to figure out if the correlation is positive or negative. How does this work? Well, I just showed you we were taking them all, and then we would multiply them together. So let's think about it like this. We said earlier that on a scatter plot, if I have a high value for X, remember we had our point here in green, it was X bar, Y bar. If I have a high value for X, let's say over here, then X is going to be a positive number. Now, if I have a low value for Y, which will be a negative, or if I have a high value for X, high value for X, it'll produce a positive number. Let's say my X value is in here. And let's say I also have a high value for Y. Let's say it's here, so the physical point would be here. I'm going to get positive times positive, which equals a positive. Now, if I, say, had a high value for X and a low value for Y, I would get positive and negative, which again, multiplied together, gives me a negative. If you continued to think through this, if I had a low value for X and a low value for Y, maybe a point down here, I would get negative times a negative, which equals a positive. If I had a low value for X and a high value for Y, I'd get negative times positive, which equals a negative. What you notice the two negative answers create are situations we described above for a negative correlation, a low X and a high Y, a high X and a low Y. Okay, and vice versa. My two positive answers when I have a high X and a high Y, or a low X and a low Y, will create positive correlations. So what statisticians said is, well, not only do we need to subtract the mean, or subtract each data value from the mean, we'll then multiply them together. And again, if all are positive, what we're going to do next is we are going to sum our formula. So I'm going to take all those positive and negative values and I'm going to add them up. And if I get a really big positive number, that's going to be a strong positive correlation. Because if you think about it, if I do this multiplication that I'm underlining in green, as I showed you above, and I do that 5 times and I get all positives, it's going to be a pretty strong positive correlation. If I would do the same thing and I get a ton of negatives, lots of highs and lows mixed together, then I'm going to have a strong negative correlation. But if I would get a mixture of positives and negatives, that's going to be a weak correlation. Means we're kind of all over the place. So then what statisticians said is, well, what if we're dealing with big data values or small data values? We're going to divide by the standard deviation. So the formula evolved into this. They divided each by the standard deviation. And finally, to average it all out, and we arrived at our formula for R as 1 over n minus 1 times the sum of y minus y bar over the standard deviation times x minus x bar over the standard deviation for x. Now, if you're sitting there and going, what in the world, Mr. Carter? I have no idea what's going on there, how you came up with that formula. It's okay. I don't need you to regurgitate to me this formula. I don't need you to calculate R by hand with this formula, okay? What I want you to kind of understand is statisticians built this formula on these principles. They recognize that differences between a positive correlation, high and high, low and low, or a negative correlation, low and high, high and low, or no correlation, a mixture of highs and lows. And they use this formula to come up with this correlation coefficient R. What this value R is going to be, and this is incredibly important, as you've been writing, I would star this in your notes. The correlation coefficient R is going to be some number between -1 and 1. Okay? Some number between -1 and 1. As I showed you up here, if we take our data values, subtract them from the mean, multiply them together, add them all up, and we get a bunch of negatives, we're going to get a number really close to -1. If you have a -1, you're going to have any number close to it is going to be a strong negative correlation. Consequently, as I showed you earlier, if we would get a bunch of positives in that formula, what our formula is going to shake out to is a +1. Any number near that, a strong positive correlation. Anything near 0 is going to be a weak correlation. That's that situation where the negatives and the positives cancel each other out. And we just kind of end up with 0 when they're all added together. This is what you need to know. If the theory sounded like I was speaking in French, it's okay. But what you have to know is the strength of a scatter plot, the strength of a relationship between two data values is determined by this correlation coefficient R. And the consequences of that are what's in blue. If you have a correlation coefficient near -1, it's going to be strong and negative. If it's near 0, it's weak. If it's near 1, it's going to be a strong positive correlation. Okay, we'll show you some examples in a second, but we got to get through some theory first. We got a little bit more theory to go. Not only do we have the correlation coefficient R, but we have the coefficient of determination. The measurement of the proportion of variation in Y that is explained by the regression line using X as the preceding variable. Or the predicting variable. What in the world does that mean? Okay? Basically, here's what it means. The amount of variation we can expect out of the Y variable based on the X variable when using the least squares regression line. Here's what you need to know for the coefficient of determination. It tells us, I'll write it in green, the really simplified version. Coefficient of determination, which is R squared, by the way. Your correlation coefficient is R. Your coefficient of determination is R squared. R squared tells us how good our trend line is at predicting data. Here's the moral of the story with the coefficient of determination. A measurement of proportion of variation in Y that is explained by the regression line using X as the predicting variable. What that's a really fancy way of saying is in 4.2, when you took your data value in part C or D in the practice and you plugged it back into the trend line and you got a Y value, well, you're doing that assuming that the trend line's accurate. R squared tells you how accurate the trend line is, okay? If R squared's a big number, it's going to be between 0 and 1. If R squared's a big number, it does a great job. If R squared's a low number, it's probably not a good job and your trend line is inaccurate. That's what it boils down to. The amount of variation we can expect out of the Y variable based on the X variable when using the least squares regression line, how good is your trend line when you plug an X value in and you get out a Y value. Okay? Okay, let's jump into an example. If your head is swimming with theory, I'm going to show you what I need you to do to apply this. Here's what I need you to do. You're going to see in your book examples, they're going to ask you to make a scatter plot. Okay? So let's say I'm looking at police presence and the amount of muggings. Okay? Police presence and the amount of muggings. So I make a scatter plot of my data. How many officers are present versus how many muggings occurred. So we'll put police presence on the x-axis, muggings on the y. And I'm going to go up by 2s. Again, if this video feels really fast and you didn't catch a concept, please go back, pause the video, shoot me an email. Let me know how I can help you. That should be a 10. All right. 2, 4, 6, 8, 10. Okay, so now we make our scatter plot. You've done this before. I'm going to go to 3, up to 5, 0, up to 8, 5, I'm going to be at 5, 2, I'm going to be at 7, and 1, I'm going to be at 9. And I get the picture of a negative correlation. Hopefully you see that. You're probably thinking it's somewhat moderately strength. So we should see a negative correlation Now, what is new to this section? We want to calculate R and R squared. What's R? Well, I want to calculate R, which is your correlation coefficient. How accurate, or excuse me, how strong of and weak of a correlation is it? Is it positive and is it negative? When just by visualizing, we can probably expect a negative, moderate correlation. Let's see if that's true. How do we calculate our correlation coefficient? Just like you did in 4.2 to calculate your least squares regression line, that y equals a plus bx, do the same thing. So I'm going to enter my data into two lists on a calculator. Again, if you need to do that, or if you don't remember how to do that, look at your formula sheet. So I go to Stat, Edit, I'm entering the data into my calculator into two lists. Then I click Stat, go over to Calc, scroll down to number 8, ling reg a plus bx, enter in the list I use. Again, if I'm going quickly, it's on your formula sheet, third thing down. And what I end up with is an R value of stat calc, one reg. I end up with an R value of negative 0.96. So actually, it was a negative strong correlation, but we were pretty close in our guess. I have a negative strong correlation. Now, you might be asked, what does this mean in the context of the problem? Well, in the context of the problem, think about it. As what negative strong correlation means that if the x is high, the y is low. Or if the x is low, the y is going to be high. What does that mean practically? A negative strong correlation means the more officers are present, the less muggings there are. Or the less officers that are present, the more muggings there are. Okay? Again, interpret our answer in the context of the problem. Negative correlation means while one's high, the other's low. And we would say this is a strong negative correlation. There is a very strong relationship between the two. It's not as if one isn't related to the other. Okay, that's our correlation coefficient. The next thing you may be asked to calculate, again, if you don't have this written down, pause it and write it down because I'm going to move on. You may be asked to calculate R squared. Remember, your coefficient of determination is R squared. Well, it tells me R squared, which I could just square R, or I could just look at it, is 0.93. What this means is if I would go ahead and plug my trend line in, which, by the way, we have the data right here to write our trend line. Remember, our trend line is y equals a plus bx. And in our data on our screen, we can see that y equals 9.62 minus 1.16 x. And you could calculate the means and plug those in. But basically here, we're going up to 9.5, and we're going down 1 over 1. So my trend line is going to run right through here. What this value for R squared means is that my trend line is very accurate at predicting my data. That if I would say go to 4, I could use the trend line to pretty accurately indicate that if 4 officers are present, there's probably going to be 4.5 muggings. Okay? R squared is high means, if I were to interpret that, means that my trend line is very accurate in predicting how many muggings will occur given how many officers are present. Again, this is just a fancy way of saying my trend line is going to do a pretty good, pretty accurate job if I pick an X value in that range like we did in 4.2 and plug it into my trend line equation. If I pick an X value and plug it in right there, my trend line is going to be really accurate. Okay, it's not going to be all over the place. It's going to be consistent with the data. Wow. A lot of content here in 4.3 that I went through pretty quickly. Please spend your time working on the practice. The theory may be a lot. If you want to reread the theory in your book, if you want additional help, let me know. But the practice is pretty straightforward, pretty calculator heavy. Okay? The big thing for you is knowing what the correlation coefficient means, how strong or weak, positive or negative my correlation is, depending on the number. Remember, -1, strong weak, or strong negative. 1, strong positive. Anything near 0 is pretty weak. Correlation or coefficient of determination, R squared. How accurate is that trend line? Okay? How accurate is that trend line? Spend your time on the practice. Please don't forget the answers are in the back of the book, so check your work. Other than that, have a great day and let me know what questions you have.